Hello everyone, welcome to Science. Ada ever looked up at the night sky and wondered how it all works? Me too. This is actually the second part of the General Relativity series and I'll be explaining more details in the next video. Forget what you thought you knew about gravity. It's not just some invisible force pulling things down like you've learned in your 8th and 9th grade. It's all about the shape of space-time itself, warped and twisted by matter and energy. Yep, things are about to get curvy. We'll be exploring the building blocks of Einstein's masterpiece, the Riemann tensor, geodesic deviation, killing vectors, the stress-energy tensor, and of course, the famous field equations. Kani nenu intha kashtapadi ee videos. Dastunnanu kadha, okaru koda subscribe cheskora. Cheskunte miku, naku, mimmalni chustunna pakkintanteki, andhariki manchidi. Let's get back to the video. Buckle up, because understanding the universe is one wild ride. Imagine a trampoline. Not the rusty one in your backyard, but a perfectly flat, infinite trampoline. Now toss a bowling ball onto it. What happens? It sinks, right? Creating a dip. That, my dost, is a simplified version of what massive objects do to space-time. Space-time is the fabric of the universe, a four-dimensional stage where everything happens. 3 dimensions for space, up, down, left, right, forward, backward, and 1 for time. Massive objects warp this fabric, creating curves. Think of it like this. You're trying to walk a straight line on that trampoline, but the bowling ball's dip throws you off course. That's gravity at work. Your path, warped by the bowling ball's mass, is actually you following the curves of space-time. So next time you trip and blame it on gravity, remember, it's just space-time playing tricks on you. Now, let's talk about measuring those curves in the fabric of space-time. That's where Riemann's curvature tensor comes in, a fundamental tool in the realm of general relativity. The Riemann tensor is a mathematical object that encodes the curvature of a manifold, a space that is locally similar to Euclidean space. In the context of general relativity, this manifold is the four-dimensional space-time, and the Riemann tensor describes how space-time is curved due to the presence of mass and energy. Imagine trying to describe the curvature of a crumpled sheet of paper with all its complex twists and turns. It's not just about how much it's bent, but also in which direction and how the bends change from point to point, creating a dynamic landscape. The Riemann tensor does exactly that for space-time, providing a detailed map of its curvature. It's a complicated beast with 256 components and kangaroo padakandi. I won't list them all. Each component tells us something about how space-time is curved at a particular point and in a particular direction, offering a comprehensive picture. Think of the Riemann tensor as the ultimate GPS for navigating the warped roads of the cosmos, guiding us through the universe's complex structure. The Riemann tensor is defined in terms of the Christoffel symbols, which themselves are derived from the metric tensor about which I explained in the previous video. The Riemann tensor is given by, as shown here. It's complex, so take your time to read and understand the formula given here. That's your classwork now. Haha. Remember those warped paths on our trampoline? They were always so fascinating to watch. One of the most important physical interpretations of the Riemann tensor is through the geodesic deviation equation, which describes how two nearby geodesics tend to converge or diverge. The equation is as shown here. And don't worry, I'll explain it in the next video. But here's the thing, geodesics that start parallel don't always stay that way. They can drift apart or come together depending on the curvature of the space. That's where geodesic deviation comes in. It's a measure of how these paths change relative to each other. It measures how nearby geodesics either converge or diverge. This concept is crucial in understanding the dynamics of space-time. Imagine 2 bowling balls rolling on our trampoline, initially parallel. They start off side by side, moving in unison. If they're far from the dip, they'll stay parallel. The flatness keeps them on track. But close to the massive center, the story changes. Their paths will curve towards each other. The dip pulls them in, altering their trajectories. This effect, my friends, is what we experience as tidal forces. It's a direct result of geodesic deviation. The moon's gravity pulls more strongly on the side of the Earth facing it, causing the oceans to bulge, high tide. This gravitational pull is a perfect example of geodesic deviation in action. The opposite side experiences a weaker pull, hence another bulge, high tide again. This dual bulging is a fascinating consequence of the moon's influence. Geodesic deviation. It's why the tides ebb and flow, and why black holes can spaghettify anything that gets too close. The immense gravitational forces stretch objects into long, thin shapes. Killing vectors. Symmetry in the chaos. The universe might seem chaotic, but hidden within the madness lies a certain elegant symmetry. And that's where killing vectors come in. Killing vectors are special vector fields that represent symmetries of spacetime in general relativity. They describe how the geometry of spacetime remains unchanged when moved in certain directions or rotated, reflecting continuous symmetries. A killing vector field is a vector field on spacetime that keeps the distance and angles, described by the metric tensor, the same when flowed along its direction. This condition is expressed mathematically by the killing equation, which involves the metric tensor and the vector field. The formula and every other Boccolo things are given here. Imagine a perfectly spherical planet. No matter where you stand on its surface, the gravitational pull is the same. That's a symmetry, and it's described by a killing vector. Essentially, a killing vector points in a direction where spacetime doesn't change. Killing vectors are crucial for understanding conserved quantities like energy and momentum. They also simplify Einstein's equations, which is always a good thing when you're dealing with cosmic level math. So, next time you see a perfectly symmetrical snowflake, remember that hidden within its beauty lies a profound mathematical truth described by a killing vector. Einstein's field equations. Matter tells spacetime how to curve. Now for the main event. Einstein's field equations. These equations are not just random symbols. They are the mathematical backbone of our understanding of the cosmos. These babies are the heart and soul of general relativity, the Rosetta Stone for deciphering the language of the universe. They translate the complex interactions of matter and energy into a comprehensible framework. In simple terms, these equations tell us how matter and energy warp spacetime, and how that warping in turn dictates how matter and energy move. Imagine spacetime as a flexible fabric that bends and stretches under the influence of mass and energy. It's a cosmic dance, a beautiful interplay between the dancers and the dance floor. The dancers, representing matter and energy, move in response to the curvature of the dance floor, which is spacetime. The equations themselves are a bit intimidating, looking like something a rocket scientist would doodle on a napkin. They are filled with symbols and terms that can seem overwhelming at first glance. But don't let the math scare you. The core concept is accessible to everyone. Now today, homework for you today is to search about these in Google. Endukante naku badhadakam, parama badhadakam. The basic idea is simple. Matter and energy equals curvature of spacetime. That's it. This relationship is the cornerstone of our understanding of the universe. Of course, the details are a bit more complicated, but that's the gist. The equations break down into various components that describe different aspects of this relationship. These equations are the key to understanding everything from the expansion of the universe to the formation of black holes. They provide a roadmap for exploring the most profound mysteries of the cosmos. We've talked about matter and energy warping spacetime. But how do we actually quantify those sources of gravity? That's where the stress-energy tensor comes in. It's like a cosmic accountant, keeping track of all the stuff in the universe that can create gravity. Imagine a box filled with gas. The stress-energy tensor tells us things like the density of the gas, how fast it's moving, and how much pressure it's under. All of these factors contribute to the gas's gravitational pull. The stress-energy tensor is like a cosmic recipe book for gravity. It tells us what ingredients, matter and energy, are needed and in what quantities to create a particular gravitational field. So, next time you're baking a cake, think of the stress-energy tensor. Okay, maybe not, but you get the idea. Black holes are the rock stars of the universe, the ultimate cosmic crushers. They're regions of space-time where gravity is so strong that nothing, not even light, can escape. These gravitational behemoths form when massive stars collapse at the end of their lives. The star's core implodes, crushing itself into an infinitely dense point called a singularity. The region around the singularity where gravity reigns supreme is called the event horizon. Cross the event horizon and you're not coming back. It's a one-way ticket to oblivion. Black holes are a testament to the power of gravity, a place where the laws of physics as we know them break down. They're a cosmic mystery, still revealing their secrets to us. Remember those ripples you create when you toss a stone into a pond? Well, massive objects do the same thing to space-time, creating ripples called gravitational waves. These waves are generated when massive objects accelerate, like two black holes spiraling towards each other. The waves carry energy away from the system, causing the black holes to get closer and closer until they finally collide in a spectacular cosmic smash-up. Gravitational waves were first detected in 2015, a century after Einstein predicted their existence. It was a groundbreaking discovery, opening a new window into the universe. By studying these cosmic ripples, we can learn about some of the most violent events in the cosmos, like the collisions of black holes and neutron stars. So there you have it, a crash course in the mind-bending world of general relativity. We've explored the curvature of space-time, the mysteries of black holes, and the cosmic symphony of gravitational waves. Einstein's masterpiece has revolutionized our understanding of the universe, showing us that gravity is not a force, but a consequence of the geometry of space-time itself. But this is just the beginning. The universe is full of wonders yet to be discovered, and general relativity is our guide to exploring the cosmos and unraveling its deepest secrets. So keep looking up, keep asking questions, and never stop exploring the universe and all its mind-blowing possibilities. Subscribe Cheskora please.